Good afternoon. I'm Jin Wang from Fudan University. I'm very honored to chair this session. I was a visiting student in Shoucheng's group back in 2008, and then later the postdoc of him from 2011-2016. So the first speaker of this session is Professor Stuart Parkin from Max Planck Institute of Microstructure Physics. Let's welcome.
Thank you very much. Of course, I'm very pleased to be here to join this workshop, and I'd like to give a talk about anti-skyrmions. Of course, I'd like to mention Shoucheng, and I knew him for a long time since he came to IBM for 3 years before he moved to Stanford, and I've been very fortunate that to have known him all this time, and of course Barbara as well. And I wanted to mention that yesterday Claudia mentioned that one of his most important achievements was bringing Claudia and I together to get married. And this is a picture at our wedding in Cambridge in 2015. And I decided, actually, thank you very much, I made this decision that maybe it would be a good idea to join the wedding with a workshop. And so the day after our wedding, the wedding took place on July the 11th, it was Saturday, and then we had this workshop you can see starting on July the 12th. And it was, so thinking backwards, on the one hand this was a wonderful idea, and on the other hand it was a very bad idea. So you can weigh these pluses and minuses. But of course, if you look closely at this long list of speakers, we had a wonderful workshop actually. Shoucheng was the very first speaker at 9 o'clock that morning. Unfortunately, I think I was so exhausted I took no photos, so I can't show you that. But anyway, it was very, very nice of him to give a talk, and he gave a fantastic talk as always. And later on, perhaps some of you know that I moved to Germany because I got married, and since then I've organized a series of workshops, mostly to try to identify people we could hire within our institute. And one of these, actually several of these workshops took place at a beautiful castle that the Max Planck Society owns near Munich. It's called Ringberg Castle. It has a lot of character. And this is a view from the castle, from the windows. And again, you can see above, you can see Shoucheng at this workshop. He gave a wonderful talk then. And of course, amongst all the very many talents of Shoucheng is he speaks perfect German. And so for me, this is amazing that he could speak so well German. I've been in Germany now 4 years, and it's very tough. It's a very complicated language with many, many rules and great difficulties. But I am told that Shoucheng spoke perfectly amongst his many talents. So of course, just like all of you, I was shocked to learn about his passing, and I really much admired him for all his talents in so many different ways. What I'd like to do then is briefly talk about these anti-skyrmions, which we have been exploring in my new institute, which is one of the Max Planck Institutes in Germany. There are 80 of these approximately. This is one in Halle, which is near Berlin. And I just, of course, wanted to advertise that if any of you might be interested in a position as a PhD student or postdoc, please think of coming to Halle. And over the last 4 years, essentially from scratch, we built up a lot of infrastructure. I'm an experimentalist, and so one of the things we've been doing is building a lot of capability to make atomically engineered materials from a wide variety of deposition techniques. And on the top, you can see this thing we call Mango, which has taken us several years to build, which has about 45 sources of variety of types for magnetron and ion beam and MBE evaporation. It's a completely automated system made in-house, but we also have some commercial sputtering systems as backups and pulsed laser deposition systems, plus a variety of molecular beam epitaxy systems, including VICO MBE. We want to look at oxide-nitride interfaces to explore possible routes to high-temperature superconductivity, as one example. But I'm not going to talk about that today. And I just wanted to point out, though, we're also interested in modifying materials, and we're doing a lot of work on liquid gating. And one of the most interesting things we're doing there is to liquid gate through patent holes in resist. And we've been able to make a whole variety of three-dimensional mesostructures on scales down to 20 nanometers, including metasurfaces that display very interesting optical properties. Again, I'm not going to talk about that. And then finally, we have a clean room. We're building a lot of devices. We've actually built this clean room, and now it's set up to do a lot of lithography using electron beam and optical lithography. Again, I'm not going to talk about that. And finally, we have optical lab, where we're using high intense femtosecond pulses of light to switch anti-skyrmions and skyrmion systems. Again, I'm not going to talk about that. And finally, I can start my talk. So I want to just give you, of course, by way of broad introduction, as you know, many of you know, I'm very interested in spintronics, and have had a lot of discussions with Shoucheng on spintronics. And one thing that he also was very interested in is taking fundamental science, really new science, and seeing how you could build interesting devices which could have impact. And of course, Shoucheng had a wide variety of interests, we've learned, and really understood how to take interesting new physics, perhaps to create devices of all sorts of different types. My own interest here is in using spin currents in particular to create new devices. And as you all know, one of the most important applications, perhaps the only important application to date of spintronics, is the use of advanced atomically engineered materials for detecting tiny magnetic fields. And this has been used in magnetic disk drives for more than 20 years. But today, the physics is no longer giant magnetoresistance, it's really spin-dependent tunneling, and it's been like that for the last 12 years. Spin-dependent tunneling junctions are useful for building magnetic random access memory. I'm not going to discuss this again, but we had a 25 years project. We first proposed this in 1995, and it's only this year that it will find wide application. Last month, Samsung announced, or actually 6 weeks ago, they announced that they were going to ship this year dense magnetic random access memory for embedded memory applications. This will be the second really important application of spintronics. But I want to talk about briefly is the third important application, which I think will take place, which is something also I proposed 10 years or so ago, which I called Racetrack memory. And this is a cartoon, which maybe some of you have seen, which is the concept that we could build a memory with up to 100 times the capacity of existing charge-based memories by building these wires which act as conduits for the motion of domain walls. And by passing current pulses on the nanosecond timescale, we can move a series of these domain walls around the racetrack so we can bring them to devices for reading and writing these domain walls. And what's interesting is that over the last 12 years since I first proposed this concept, first we demonstrated it about 10 years ago, but in the last 5 years using spin orbitronics, we and others have demonstrated that we can move these domain walls with current pulses 10 times more efficiently than was even possible just 3 or 4 years ago. And this is why today racetrack memory is of interest to nearly all the major memory companies around the world. They're all interested in potentially working with us on taking the basic science that we believe is at the point where one could imagine building a technology based on this concept. So I wanted to briefly discuss just a couple of what makes this possible. One of the most interesting phenomena is this idea that magnetic moments through exchange don't have to be parallel or antiparallel, or in frustrated antiferromagnetic systems they can be triangularly arranged, but in a variety of systems, either from bulk interactions or in multi-layers, you can create systems in which the magnetic moments want to be oriented at roughly 90 degrees to one another in a vector chiral manner. This is just shown in this cartoon. If we take a layer of cobalt, for example, on the atomic scale and place it on a layer of a heavy metal like platinum, tungsten, tantalum, then that interface gives rise to a chiral vector interaction that causes the domain walls in a perpendicularly magnetized film to be either clockwise or anti-clockwise in their nature to be nail domain walls in which the magnetization, as you can see in this cartoon, rotates from an up to a down direction by rotating in a plane perpendicular to the domain wall, as opposed to a block domain wall where the magnetization would rotate within the wall itself. That's favored by dipole interactions. So this Dzerzhinsky-Maria interaction at interfaces, which was first observed in using spin-polarized tunneling in Wiesendanger's lab many years ago, has now proven to be critically important for racetrack memory. By these chiral domain walls, they can be moved with current much more efficiently than using, for example, torques from currents polarized within the magnetic layers. But this interaction works by stabilizing the chirality of these domain walls along the racetrack in conjunction with something else you're all very familiar with, the spin Hall effect. And again, what's surprising is that this was first observed in semiconducting systems maybe 15 years ago, very, very tiny conversion efficiencies of charge to spin current. But again, in the last 3 or 4 years, there's been some very interesting developments, and even simple metals like platinum and certain forms of tantalum and tungsten generate efficiencies once you take account of the transparency of the spin current to a magnetic, non-magnetic interface. Then the efficiencies are of the order of 10 to 30%. So these charge to spin current efficiencies are much larger than was anticipated just a few years ago. And the spin Hall effect is also a chiral effect. And it's the combination of these chiral effects that really makes it possible to use currents to switch them to spin currents. These spin currents diffuse into these chiral domain walls. And because of that chirality, all the domain walls along a racetrack will move at the same direction. And as we've demonstrated, up to speeds of more than 1 kilometer per second at useful current densities. This is why racetrack is interesting. So I'm not going to say much more about racetrack. Here you can see, for example, 20 domain walls moving backwards and forwards in a single racetrack, cobalt, nickel, cobalt layers, each a few angstroms thick, which we can make using simple techniques. But below you can see the most interesting one, and the only way to technologically make racetrack is to eliminate all long-range dipole fields, which otherwise cause the domains to interact. And we can do that, as you can see down below, by building a structure of 2 racetracks, one on top of each other, coupled through an ultra-thin layer of ruthenium, which is, again, something I discovered 30 years ago, which is that you see an oscillatory, long-range coupling through ruthenium. And for thin layers in the range of 2 to 7 angstroms, it's antiferromagnetic. So we can make one racetrack with perpendicularly magnetized domains, these nail domain walls, and there will be an exact mirror image in the upper racetrack. So we can design it so that in net, aggregate, each domain consists of 2 domains in opposite directions with no net magnetization. And therefore there's no interaction, no dipole fields. And this is what makes racetrack possible. This is very interesting, I think. We call this a synthetic antiferromagnet. So now I want to switch from chiral domain walls to something that's attracted a lot of attention, again in the last maybe 5 to 10 years, which is the notion of a skyrmion. So the racetracks I mentioned are perpendicularly magnetized layers. But in any system in which you have a perpendicular magnetization, the ground state, because of demagnetizing effects, can form basically domains which are oppositely magnetized. And a skyrmion is a very special way of demagnetizing a system in which you have a magnetized, perpendicularly magnetized system, and you form circular regions in which the middle of those regions are magnetized in the opposite direction, but the wall has a chiral nature, just like the chiral domain walls stabilized by this interface Dzerzhinsky-Maria vector. Here it's typically a bulk Dzerzhinsky-Maria vector in non-centrosymmetric materials or even chiral materials that stabilizes these skyrmionic objects. So on the left-hand side you can see a block skyrmion. In this case, the wall surrounding this reversed region of magnetization is a block wall. And I think you can see in this cartoon that means that the moments in the wall itself will be oriented around tangentially to the circumference of this typically circular object. On the right-hand side, you can see a nail skyrmion. And in this case, the magnetization in the middle of the wall is oriented along the radius. I think you can see that in these two cartoons. Both of these objects have been discovered in a number of distinct material systems over the last 10 years, from the original observation of skyrmions in manganese silicon, which is a chiral system. Now, what we discovered 2 years ago is the middle object, an anti-skyrmion. So let me try to explain what that is. And that is a system in which, as you move around the domain wall, the wall around the circumference of this circular object, the wall changes from being a block wall to a nail wall to a block wall, etc. And every time it changes, it reverses its chirality. So it consists of segments of block and nail walls of opposite chiralities around the circumference of the object. And this is because of the point group symmetry of this particular material in which we find this object. It means that the Dzyaloshinskii-Maria exchange interaction has to have certain signs and magnitudes around the circumference of this object, depending upon the crystal direction. So the anti-skyrmion structure is connected to the underlying crystal structure. So along certain crystal directions, you have block walls, and along certain other directions, 45 degrees, you have the nail walls. So we detected this anti-skyrmion using a very conventional technique, Lorentz transmission electron microscopy. So in our aberration-corrected microscope in Halle, we essentially pass 300,000 volt electrons through a very thin sliver of the material. We form this from the bulk material. And as the electrons cross this material, then the in-plane magnetic fields or magnetization causes motion of the electrons to the left or to the right. And this leads to distinct patterns for each of these objects. So this is what we can calculate the patterns to be. So in the middle, we can actually use micromagnetic simulations to include exchange anisotropy and the Dzyaloshinskii-Maria exchange, Eisenberg exchange, anisotropy, dipole fields. And we can calculate these respective structures. And then we can calculate what we expect to see in the Lorentz microscope, depending upon the focus of the electron beam with respect to the plane of the sample. This is shown here. On the right-hand side, you actually see nothing if you look at a nail skyrmion, because the electron beam is displaced around the circumference of the object, so there's no change. The block skyrmion you can see on the right, on this side, looks like a white blob, a region of increased electron intensity in the middle of this blob. And that's what's been seen by, first by Takura and his group in the Riken, in iron germanium at room temperature. And the anti-skyrmion we calculated should look like this. You see two lobes of increased intensity of the electron beam and two lobes of decreased intensity, like a clover leaf structure. And this is what we were able to see in a material that Claudia discussed this morning, these Heusler materials. And as she mentioned, then my interest has been for a long time Heusler compounds which have large anisotropies, so that the magnetization wants to be perpendicular to the tetragonal plane of certain of these tetragonal Heusler materials. And it turns out these materials have a certain symmetry, D to T, point group symmetry, that should stabilize anti-skyrmions. And indeed, that's what we see in these systems. I want to discuss those briefly. And the work that led to this was that these materials, for example, manganese 2 rhodium tin or manganese 2 platinum tin, they consist of structures in which you have alternating layers of the manganese plus rhodium and then manganese plus tin, and they're ferrimagnetic. One layer is oriented with this magnetization antiparallel to the next layer. And there's a whole family of these materials. Magnetization looks like this. As you reduce the temperature, you see Curie temperatures close to or above room temperature. And we had some evidence from anomalous Hall effect that there was a topological Hall effect characteristic of anti-skyrmions or skyrmions in this manganese 2 rhodium tin material. Well, where we first saw these anti-skyrmions, we published this in Nature like 18 months ago. You can see on the top left, can you see this picture? This is the Lorentz micrograph, and I think you can see that it looks pretty much like the calculated pattern. You see two white lobes and two black lobes, cloverleaf. So it's a beautiful, direct determination that we have anti-skyrmions. And typically, when you form these anti-skyrmions, they appear in arrays like this. You can see an array of these objects, an hexagonal array, And these are different, how they look as we vary the field and temperature within the microscope. And that's what I'd like to briefly discuss. So obviously, as you increase the magnetic field, eventually you eliminate these antiskyrmions because the magnetization all becomes parallel to the magnetic field. And that you can see here. And you can see here on the edge of this device, you can see a row of antiskyrmions. And so as you increase the field, you start to eliminate the antiskyrmions, but depending upon the thickness of this lamella, then there's a different phase stability. I want to come back to that. This is just showing you this. Now, by the way, this material we're looking at is a little bit complicated. It's not manganese 2 platinum tin, it's manganese 1.4, platinum 90%, palladium 10% tin. And this is for reasons that not possible to stabilize the material with all the manganese sites filled. The phase diagram is shown here. This is the temperature. The lowest temperature we can achieve is 100 degrees up to 400 degrees. And you can see this is the perpendicular field. And at low fields, you actually see a different structure. I'll mention a helical structure. And then you see a wide range of temperature where we see these skyrmions are shown here. Now, I want to briefly mention, so to look at these structures, we actually make from a single crystal, we cut a layer which can vary in thickness from 50 nanometers up to several microns. And we've been exploring the current-induced motion of these antiskyrmions. I'm going to skip that because we're running out of time. What I want to focus on is the dependence of the phase diagram on the thickness of this material, which you might think is not so interesting. Turns out it's quite interesting. So we basically make, using focused dye milling, here is an 8 micron by 8 micron lamella whose thickness varies across the lamina as shown on the left-hand side, and we measure the thickness locally using electron energy loss spectroscopy intensity. And you can see here then is that wedged lamella, and we're going to take 3 regions with different thicknesses, A, B, C, and as we vary the thickness from the thinnest A to the thickest, and we look at the skyrmionic antiskyrmion we see as a function of magnetic field, you can see distinct differences depending upon the thickness of this material. So I want to come back to. And then what we find out, we can map out the whole phase diagram, the field temperature dependence at different thicknesses. And the most important point is that we see that there's a wide stability region of antiskyrmions independent of the thickness. On the right-hand side, in a B20 chiral iron germanium system measured in the Riken in Takura's group, and they found that as they increased the thickness just slightly, the red region, which is the skyrmions, again, as a function of temperature and perpendicular field, this region shrinks even as the thickness is increased from 15 to 75 nanometers, almost disappears. On the left-hand side, you can see great stability of antiskyrmions as a function of field and temperature. So why is this? So we can actually carry out micromagnetic simulations. And what you see for, depending upon the thickness, here this is a certain thickness, as a function of increasing field from the top left to the bottom right. Bottom right is all red, everything is magnetized. Top left you can see both antiskyrmions and the stripes which are representative of the helical system in which this can also form. So we can then explore as a function of thickness from simulations what we expect to see. And now in these simulations, of course, we include the appropriate symmetry of the Delezinski-Maria exchange vector. On the top, we compare the cubic B20 chiral system, and we find that as we increase the thickness, which is from top to bottom of the top left, you can see the dashed white curve shows you where we see skyrmions. And as you increase the thickness a little bit, you see they disappear. Whereas the antiskyrmion in the same simulation, you can see there's no dependence of the region where antiskyrmions are stabilized as a function of increasing thickness. Very simple to understand. In these D2D systems which stabilize antiskyrmions, there is no variation of the Delezinski-Maria vector component in the tetragonal direction. So that means independent of thickness, there's no reason why the antiskyrmion structure should have any twisted structure in that third direction. Whereas a cubic system, the B20 system, in all directions you should modulate the magnetization. So you should expect that you should make the skyrmion's tubes disappear as you increase thickness. This is what we find. So we think this is a very fundamental point. Back to the most interesting thing. We see, as I mentioned, the skyrmions appear from a helical phase. So in the Lorentz microscope, a helical phase appears as alternating black and white lines. And in the anti-skyrmion system, those directions of the helix are set by the crystal axis directions. And we find this helical period increases with thickness. This is very dramatic. Here is a wedge. You can see 8 microns long. Thickness is varying from a few hundred nanometers to about a few hundred nanometers. And you can clearly see, I think, that this is where we see the helix. We've oriented along the long axis of this wedge. You can clearly see that the separation of these helical, where the magnetization goes up to down, it's much smaller, the period, than here at the thicker end, where it's much wider. And similarly, if we appropriately use a magnetic field and to stabilize the anti-skyrmion structure, you can see the anti-skyrmion's size is increasing from a small size for thin layers to a much wider size for thicker size. So I'm running out of time, so I'll just show you. In Lorentz, we can only go up to about 400 nanometers, but using magnetic force microscopy as a function of temperature, we can make wedges which go up to thicker distances, and then it's even more dramatic. This is a profile of the magnetization in the helical phase, and you can see the period is varying from 95 nanometers at one end, the thin end, to half a micron at the thicker end, and it's even more dramatic. This shows you just a summary. The period increases linearly with thickness, it seems, and now we can go to even thicker, up to 4 microns, and we still see a continuously variation of both the period of the helical phase and the size of the skyrmion, ranging from here 100 nanometers up to more than a micron. And that means that we can actually observe these objects using Kerr microscopy. This is just to show you the same wedge where we've now stabilized the anti-skyrmion phase by just tuning the magnetic field. And we find that the size of the anti-skyrmion and the period of the helix are in 1-to-1 accordance, and both of them increase in this linear fashion with magnetic field. Since my time is up, I'll say we can actually now then observe all these structures in single crystals using both Kerr microscopy and magnetic force microscopy. And we have, of course, we can calculate what is the reason for this. And the reason is, it turns out it's completely due to dipole energy, long-range dipole fields that in these thin layers cause suppression, cause shrinkage of the structures. As we increase the thickness, these dipole fields become less important, and then we actually see the size reflected by the ratio of the Heisenberg to the Delizinski-Maria exchange. So I don't have time to discuss that, and I don't have time to tell you that we've also seen anti-skyrmions in a manganese to rhodium tin over a more limited field temperature range. And I won't tell you, we can now make thin films of these Häuslers, 1 and 2 unit cells thick, using a chemical templating technique that we recently published, and we're searching intensively for anti-skyrmions in thin layers, which we can then move using spin currents generated through spin Hall effects in heavy metals. We hope to see that shortly. So let me just summarize. I'm sorry I ran out of time. Magnetic anti-skyrmions we've observed for the first time, now in more than one tetragonal inverse Häusler, and they have this unique property compared to skyrmions that have traditionally been seen, that their size can be dramatically varied. Very useful, potentially, for technology, simply due to long-range dipole fields. And by the way, I don't have time to discuss this, but recently we found another system related to Häusler, platinum manganese gallium system, which we actually see skyrmions. And in that case, it has a different symmetry. It's a trigonal system. And then we can also see a size variation of these skyrmions, which also is potentially very interesting. And I think this could be useful for racetrack memory. Anti-skyrmions are much more interesting for applications than skyrmions for some technical reasons. Happy to discuss. I'd like to thank the colleagues, my students and postdocs, and my institute in Halle, Claudia and her group, for providing these samples. And I'd like to thank you for your attention.
So question and comment?
Hi, I have a question about that Racetrack.
Yeah.
You know, the industry now really needs lots of storage. I personally, I believe in 10 years after the 5G, 6G, our cell phone need terabyte, 5 TB storage. And the industry really want to have a fast as a DRAM, but as cheap as a SSD or even the hard drive. So how is the Racetrack memory compare the speed and the price?
So it turns out, so we're actually talking to Samsung about having a project together, and they have told me that they believe that we can compete with VNAND, which is the densest memory today, the cheapest memory. Samsung is the leading manufacturer of such memory. But this is basically where you take a series of flash memory cells and you pile them one on top of each other. They can do that 128 times. And then you build vias to access those cells. But that technology, like all charge-based technologies, is limited by size. It's already reached the end of its roadmap, which is why they're building these vertical NAND structures. So if we make a few layers of horizontal racetrack, we can compete with VNAND, providing that we can put these domain walls close enough together. Otherwise, it looks very attractive, actually. So I think this is the only memory on the horizon that could compete with VNAND. And I think since currently the amount of work, let's say the numbers of people working on Racetrack is like tiny, let's say compared to the field of topological materials. But nevertheless, so maybe with a few more people working and exploring other materials, I think it's just a question of finding, well actually I think the materials we have already would be good enough to build a memory that could compete with VNAND. You have to, the limitation is currently all our work is from optical detection of these chiral domain walls. We have to go well below those dimensions to make a real device. In principle, it's totally possible. It just requires a lot of engineering effort. You need to basically put domain walls perhaps 10 to 20 nanometers apart in racetracks which are 20 nanometers wide. That's what you have to do, which is totally possible.
Okay, Daniel. Oh, Dan. Yeah.
Just a while back, by writing and deleting skyrmions using STM. Can you? Is something similar possible with the anti-skyrmions?
Yes, so we've actually have deleted anti-skyrmions using local tips. For example, in our magnetic force microscope. So you're referring to Roland Wiesenthaler's work, where he used spin currents to create and read skyrmions. So I think we could do the same thing with anti-skyrmions. It's not clear whether technologically you suddenly not want to use a scanning dulling microscope, but of course you can build local devices where you can inject currents to write anti-skyrmions.
Okay. Question?
So can you describe the coupling of current to any of these structures, to anti-skyrmions, or because you talked about being able to flip these with current?
Yeah. No, I didn't talk about that. No, I didn't. I talked about moving chiral domain walls with current. I said in anti-skyrmions, we've attempted to move them with current in these bulk materials, but we haven't seen any motion except for thermally induced motion. So, but what we're sure is that, so these are, for example, images you probably can't see, but if you look extremely closely, you will see the anti-skyrmion lattice. You see it moved slightly from current pulses that were passing through thin slivers. But we believe this is mostly due to temperature. However, we can calculate that if we have spin currents through spin orbit torques from neighboring layers, then they should move. And anti-skyrmions are very interesting because depending upon the crystal direction, the current direction, they will move to the left, to the right, or in straight lines. Unlike skyrmions, which will always move to the left or to the right, depending upon their chirality. So in that sense, these anti-skyrmions solves a very important problem with the use of skyrmions, that they don't move in straight lines. But anti-skyrmions can. We haven't demonstrated that yet, but we plan to do so as soon as we can make thin enough films.
Okay, one last question.
Thank you. So touching upon the previous question, I think skyrmion you can detect it via topological Hall, skyrmion Hall. And what about this? And also, in relation to real applications, how do you read it out, the anti-skyrmions?
So I think this is a very interesting question. So the topological Hall effect is certainly very interesting. However, from a technological point of view, the signal is simply too small to be useful. So you have to think of some other technique. So we're not, whilst we're exploring, of course, topological Hall effects in these systems, those very interesting from a science point of view, but technologically not at all useful. But there are other things you could do. For example, you could use the anomalous Hall effect potentially, which is much, much larger. In some of these engineered structures, we can engineer the anomalous Hall effect. So even in a synthetic antiferromagnetic racetrack where there is no net magnetization, so the zero moment, but in fact we can have giant anomalous Hall effects by slight asymmetries in the structure. So it's a very interesting question, but currently not possible, I think, technologically to do that.
Okay, since time is up, let's thank Stuart again.
Okay, thank you very much.